Min forskning fokuserar på tekniska lösningar för att sluta kretsloppet mellan stad och land.
Vi forskar på teknik som möjliggör att man kan samla upp växtnäringen från avloppet och använda den till att producera nya gödselmedel.
Hej, jag heter Björn Winnerås och jag är professor i kretsloppsteknik vid Institutionen för energi och teknik.
I dagsläget så produceras växtnäringen i storskaliga industriella processer och kommer till lantbruket i form av mineralgödsel. Och till slut så kommer den då ut i vårt avlopp eller i vårt matavfall. Globalt är det bara avloppsvattnet från var 10:e person som behandlas på ett avancerat sätt. Resten släpps ut mer eller mindre obehandlat till våra vattendrag och våra hav. Och det leder till stora problem med övergödning och även syrebrist i haven.
I samma regioner har man dessutom problemet med att man inte har tillräckligt med gödselmedel, vilket leder till att jorden blir allt mer utarmad.
Och just i den skärningspunkten så kommer vår forskning in. Att försöka hitta sanitetslösningar som fungerar för alla och samtidigt producera gödselmedel som är användbara för lantbruket.
Vi forskar på att producera koncentrerade gödselmedel genom att torka urin. Det här har lett fram till att vi har utvecklat ett system som man kan installera på sin egen toalett.
Om vi samlar in all urin i Sverige och återför den till lantbruket så skulle den kunna ersätta upp till hälften av den mineralgödsel som vi idag importerar. Och det gör att vi kan få ett mer uthålligt samhälle och förbruka mindre av de ändliga resurser vi har.
Vi måste ställa om till ett cirkulärt samhälle och det känns otroligt viktigt för mig med min forskning att bidra till den omställningen.
Welcome to the broadcast, Björn Winnerås.
Thank you.
Clean water and sanitation are in focus for your research. What made you interested in this subject?
I would say it's the combination of both sort of working with the environment but also having this process engineering and chemistry in the background. So it makes sort of a full picture and that we actually can make change.
And when did it start for you, this interest?
I mean, I have had an environmental interest for a very long time, but I mean, I started working with this topic almost 25 years ago. So it's been quite a while.
Quite a while, yes. The 6th UN Sustainability Goal is that all people should have clean water and sanitation. What would you say are the challenges in trying to reach this goal?
I mean, providing water, we are getting quite close, I would say, and it's advancing quite fast. So it's most of the population in the world has access to clean water. But the challenge is to take care of the wastewater because it's much more complex and we also have so many people that doesn't have access to a proper wastewater treatment.
And those two factors, water and sanitation, how are they interlinked?
I would say, I mean, they are linked by the water and in the end, if we don't treat our wastewater, it will actually have the end effect that we will pollute our drinking water, both surface water but also groundwater, and therefore we may, if we not actually fulfill the wastewater part of it, we will actually destroy the drinking water part as well because we will not have access to clean water.
And this is where your research makes so much sense, isn't
Yeah.
it? Yeah, so why don't we listen to your lecture? Please
Yes.
enter the stage, Björn. And then I would like to introduce Björn Winnerås, Professor of Environmental Engineering, and he's going to talk about technology for safe nutrient cycling. Please, Björn.
Thank you very much. And I would like to start with, before I talk about my research, I would like to also mention my research, the group that I'm doing my research together with, because they are a very important part of what we're doing in our everyday work. And the results that I will present today is not only I that have done it, it's several people, so thank you. And I would like to start with looking at why do we have wastewater treatment. I mean, it started 150 years ago where we tried to get pathogens out of the city and to increase the public health. And that has been quite successful, and it's still successful. But piping the wastewater out of the city into the water recipient also led to several different problems, where we got issues with eutrophication and other pollutants. So during the last 100 years, we have developed the wastewater treatment step by step to removing these problems. But as I mentioned before, the focus of my research is to recycle the plant nutrients. But plant nutrients per se is not the factor that is driving the wastewater management. And the reason is that the resource of the plant nutrients, the value of them is not that high. If we take the nitrogen, for example, then we have 1 kilo of nitrogen cost for a farmer costs approximately €1 or 10 kronor. But then when we take it to the wastewater treatment plant, then it costs approximately 10 times more to remove it. So it's 100 kronor. And the case for phosphorus is the same. So we have to do quite a lot of treatment, and the cost is very high to remove. And during the life cycle of the active nitrogen, it's also generating quite a lot of pollutants. For example, during the Haber-Bosch process, when we extract the nitrogen from the atmosphere, we release quite a lot of greenhouse gases. And then at the end, from the wastewater treatment plant, if we don't remove the nitrogen, we have a problem with eutrophication in the environment. And here in Sweden, we have quite advanced wastewater treatment, but if we look globally, it is approximately only 10 to 20% of the global population that has an advanced treatment. So many streams in the world is actually looking like this. So you can see here that the water is more or less only wastewater that is coming out, because we have a linear flow and the treatment is minimal, and therefore the recipients becomes polluted. And in dry areas, the streams are more or less only wastewater because you don't have any other water source. And this is also leading to that we have a problem with a lot of pollutants that actually can affect, like we discussed just before, that the wastewater flow is actually polluting the drinking water. So the access to drinking water is very complicated. And if we look into the flow of water today, and if we have the case of Uppsala, we take the water from the river Fyris, and then we treat it, and we get a very nice drinking water. And then after we have taken the drinking water and drinking it, we will actually, it goes through the body as we have a mass balance, and it ends up in the wastewater. And then the question is, where does the wastewater end up? It ends up back again in the river Fyris. Of course, it's downstream compared to where we extract the water, which is upstream of Uppsala. But the water from Fyris is coming out into the Lake Mälaren. And in Lake Mälaren, we have a lot of wastewater coming in. We have Västerås, Eskilstuna, and several other bigger cities that is contributing with the water, with wastewater. So the estimation is that approximately 5% of the water in Lake Mälaren is actually wastewater. But we have advanced treatment in combination that the lake is quite big. So therefore and then we have the nature-based treatment in the lake. So the quality of the water in Mälaren is quite nice. And that is good because the drinking water of Stockholm is taken from Lake Mälaren. So then we have, in the drinking water of Stockholm, we actually have approximately 5% wastewater, so that we have this closed circuit already. But we have advanced treatment again and a clean water, so the drinking of water in Stockholm is safe to drink. But we have more and more reports about findings of pharmaceuticals in the drinking water. And this is because the treatment plants we have and the nature-based treatment is not possible to remove these substances from the wastewater. So we find pharmaceuticals in the drinking water. So the way I would like to deal with this is to actually make an off-grid system so that we don't have a wastewater that is generated, so that we have the water circular inside the house. Which means that when we build our house, then we fill the house with water, and then we use the same water over and over again. But going off the grid, most people imagine this kind of system, where we have, like these kids in Kampala, where on their way to school, they are visiting a spring, and then they're taking the water they need in school and bring with them. And when we look at the toilet, that we place a latrine very far away from the house, so that we make sure that we don't have problems with smell and insect and so on. But when I look into an advanced treatment system, I see it, it's off-grid system, I see a much more advanced system, where we have a treatment plant and a storage centrally, that we have the same water that we use. So if we have a storage of 1 meter cube, we can actually have 10 days of water capacity for one person. And then we can use a laundry machine, we can take our showers, but we can also drink the water because we have a clean water that we have produced. And then we generate the wastewater that we are treating step by step and producing a clean water fraction. And taking into what the research is, I will take just one little spot of this and looking into the urine treatment, where we have developed a system that we call alkaline dehydration, where we produce the fertilizer and a clean water fraction out of the urine inside the toilet. And this is how it can look like. So the user interface is still the same. It's a flush toilet. Of course, it's a urine diverting flush toilet. And you have the treatment unit below the toilet seat. And I will focus quite a lot on nitrogen here, because 80% of the nitrogen in the wastewater is from urine. And I would say most of the nutrients that coming out of society, of urban society, is actually waste from the wastewater. And then the major contributor is the urine. And 80% of the nitrogen in the urine is in the form of urea. And in a normal urine diverting system, the urea is degraded by enzymes from the biofilm and converted into ammonia and carbonate. And if we want to dry that kind of urine, then we will also remove the ammonia, and we will not have a full fertilizer that is produced. So what we do with alkaline dehydration is that we block this enzyme activity by introducing high pH. We can do that by adding lime, for example, or magnesium oxide. And if we use magnesium oxide, we can also play with the chemistry inside the urine, so that the ammonia that we also excrete, a few percent, that we can precipitate together with the phosphorus we have in the urine and with the magnesium and produce magnesium ammonium phosphate, which is struvite. And by that, we actually capture all the nitrogen in our system in the drying bed. And in this treatment, we also have to have in mind that we have a risk of pathogens. Because if someone is sick, you will excrete pathogens, and it will end up in our toilet. And doing so, by having just urine diversion, we take away a lot of the risk with pathogens, because most of the pathogens are found in the feces. But we will also find some of the pathogens just cross-contaminating the urine, so we have to deal with them. But here we have once again the advantage of having a high pH. So the high pH is actually inactivating viruses and bacteria very efficiently. Parasites are a bit slower, but still they are inactivated. So having a storage time after the treatment, then we actually get a clean product regarding pathogens. However, pharmaceuticals is not removed in this kind of system. So we have to deal with the pharmaceuticals if we want to remove them. But the advantage is that when we do this concentration and take away the urine, we have a very small fraction. It's only 1.5 liters per person a day. And therefore, we can actually treat and remove the pharmaceuticals either inside the toilet or in the drying bed, or in the end process where we produce a clean fertilizer. So when we do this, we actually concentrate the urine 20 times. So instead of having 1.5 liters of urine that we excrete per day, then we actually get only 80 grams of pure fertilizer that we can use. And that fertilizer is actually of a grade that is comparable to a mineral or chemical fertilizer that you buy in the store. So it contains approximately 15% nitrogen, 2% phosphorus, and 5% potassium, so that we can use in conventional agriculture. So instead of being a pollutant going out into the environment, we are producing a clean fertilizer. And that clean fertilizer is approximately, if we take all the urine we have in Sweden, then it will replace approximately 25% of the nitrogen that we're importing today as a mineral fertilizer. And if we look globally, you can see in the darker areas, then the potential is even higher. And if we look globally, the potential of replacement is somewhere between 25 and 30% of the plant nutrients. So the potential in the urine, instead of being a pollutant, being a resource, is really high. But as with all new system, it's several challenges if we want to implement this. First of all, it's technical. As I mentioned before, we have worked quite hard during almost 15 years developing this system and trying to find it to work. And now we are reaching how we can start to implementing it. And all other parts of this kind of system where we want to have a circular flow will need several development steps to find a workable a system that actually works. But it also have a big challenge with acceptance, because you have to get people to accept that you will drink the same water that you used to flush your toilet yesterday. And this is a major challenge with this kind of system. But it also gives a lot of opportunities, because if you are aware of that the water I have today, the water I will drink today is the water that I had yesterday as in my toilet, for example. And therefore it's also incentive of not pouring stuff into the toilet that should not be there. And you will also, having this kind of system, you will always provide a pure drinking water every day. And not like it have been here north of Uppsala, where it been several smaller cities that have not been able to drink their water for several months because it was a pollutant in the water. But here you will have the clean water, the same water in your house every day, and you will not generate any pollutants because you would not have any wastewater that you generate. And where are we with this research today? We started over 15 years ago with the development of this kind of system. And a year ago, we actually installed our first pilot system at our department here at SLU. And we have been running it for over a year and testing it and implementing the research that we're doing in the lab. And that have actually made us, so that have come so long, so that we actually can have our first system installed at the headquarters of the wastewater company in Malmö, which means that we have the first generation of a alkaline urine dehydrating system that will be outside the university and that will be implemented for a long term. And this, as I see it, this is the first step towards a sanitary revolution where we actually have a wastewater system that is not generating any wastewater. It is only generating clean water and a fertilizer. And the advantage with it is that the clean water will mean that we have clean water both in our house every day, all the time. But it will also mean that we will have clean water in the environment because we don't let any wastewater out and we will not pollute the water recipients. Thank you.
Thank you very much, Björn Winnerås, and welcome back. And please don't forget to email us your questions, nyaprofessorer@slu.se. How interesting.
Thank you.
You got into the psychological obstacles a bit, to handle, to make a system, a small system, circular system locally. How big are those obstacles, do you think, for people to have overcome?
I think they are quite big today. But at the same time, it requires quite a lot of discussion. Because I've heard a lot about when we was introducing, for example, source separating of solid waste, that during the 80s, the discussion was that no one would ever imagine to sort their solid waste. And today, I mean, this is the everyday duties of all of us. Mm-hmm. And I don't hear that many people complaining about that.
No.
So I think it's a lot of information, and it's also a lot of getting people to understand why we are doing this.
Yeah, to raise awareness about why. Yeah. We have a question here from the audience. Do we need all this chemistry to purify water? Can't we just use distillation to clean water? Or does that cost too much energy?
I would say the energy is a challenge, of course. But distillation is one way of doing it. But at the same time, we need to have the salts in the water and so on. And it's also quite complex material. And as I understand it, on the space stations, they are using distillation. Mm-hmm. But it's something it's one alternative, but it's very energy intensive. So you have to have in mind the pros and cons
Yeah.
of different systems.
Well, the sanitary solutions you're working with, how could they be applied in Sweden in a large scale?
So the first reaction I often get is that, oh, I would like to have this in my weekend house or summer house. But I see it as a much bigger usage, that it actually can be also used in a normal home. When you build a new home or you renovate, you can actually install this kind of system in your normal home as well, even in the city center, I would say.
Okay, and in a larger scale, what could it look like? How could a system work?
I mean, the typical discussion is that many wastewater treatment plants is reaching the capacity. And if, like, we have these exploitation areas, like here in Uppsala we have Ulleråker, and in Malmö they have Seger Park, and they are if they want to connect to the sewer, they are quite soon reaching the capacity of the sewage treatment plant, and then they have to build a new sewage treatment plant, and that is very expensive. But if we can remove the plant nutrients from the wastewater, then we actually have a much more capacity of the wastewater treatment plant, because a lot of the capacity in the plant is taken by removing the nutrients. And if we do that in advance, then we actually can have a much longer capacity of the treatment plant.
So how far away are those solutions that you're talking about?
I mean, we are installing the first system now in Malmö, and we will also have installation of public toilets in Visby in Gotland during this summer. And as I see it, this is the first step, and that it has also been a policy decision, for example, in Paris, where they actually have said that they will install 1 million urine diverting toilets during the coming 20 years. And that is one way of looking at it also, that major cities is really looking into this as a solution for the future, because they see the limitations in the current treatment plants.
Thank you. We have a few questions here from the audience. Perhaps an obvious question. What is the fate of pharmaceuticals in the urine system?
You will get a lot of pharmaceuticals in the urine system, because most of the pharmaceuticals we consume are we actually excreting in active form. So they will be there. But as it's such a concentrated fraction, we can also treat it. And we are looking quite a lot into, we have one PhD student looking into how we can actually remove the pharmaceuticals out of the urine within this dehydration system, and therefore actually producing a clean fertilizer without the pharmaceuticals. So, and this will make it, as we have a concentrated fraction, it's much easier to treat compared to if we have the very diluted fractions that we have at the wastewater treatment plant.
Oh, yes, of course. Another question here. How do you achieve hygiene when recycling water in a building as drinking water? And how to monitor that the system is in fact working?
I mean, this is one of the challenges I would say for the future. But you have treatment systems. I mean, today you have, if we look globally, a lot of the water that people is using is actually filtrated, so that you have a local filter producing clean drinking water. And they are advanced. And to make sure that you have a clean water, that is a lot of process monitoring, so that you have a functional process. And if you have a functional process, you can actually have process parameters that you see. If I fulfill these process parameters, then I actually don't have any pathogens in my water. And therefore it's quite easy to monitor that you have a safe water source.
So that wouldn't be a very big issue then?
No, I would say it's even safer than having the tap, because you don't really know what have happened with the water before it enters your house.
So a more sustainable solution,
Yes.
maybe. Well, we talked about implementing these kinds of systems in a city or so. But if you look, if you take a global perspective, what is the potential, or what do you think?
I would say the potential is great, especially as we only have 10 to 20% of advanced treatment of the wastewater. We are generating so much wastewater, and we have very limited clean water resources. So by implementing this kind of system, it can actually be not that high price. We are looking into very simple solutions as well. And then you're producing sort of a clean water source, and you're not polluting the environment. So therefore I see can actually be the future in many countries. And then also you can have local production of fertilizer that you not have access to.
And here,
today.
thank you. And here we have a question about fertilizers. Are you in contact with fertilizer companies that produce a marketable fertilizer out of it?
Yeah, we have discussions. I mean,
Okay.
but we are just in the beginning of the production unit. If we look at the fertilizer companies, they talk millions of tons, and we are not really there yet. So, I mean, getting the attention of the fertilizer companies has been a challenge, but we are in discussion, yes.
Okay, how exciting. Well, I guess we don't have any more questions from the audience, so I think I will say thank you very much for attending the broadcast.
Yeah.
Thank you, Björn.
Yeah, thank you very much.